Let f of x be some infinitely differentiable function, let's say sine of x. What if you wanted to approximate sine of x for values of x close to 0 using a polynomial function? First, let's graph sine of x and approximate sine of x to a quadratic degree. Now all we have to do is find the coefficients c0, c sub 1, and c2. If our function is going to be any good near x equals 0, it has to be exactly right at x equals 0. Sine of 0 is just 0, and f of x, our approximation, at 0 is just c0. Thus, c0 has to be 0 if we're setting the equations equal to each other. But you know what would be even better? If the derivative of our polynomial matched the derivative of sine of x for values of x close to 0. Evaluating the derivative of our polynomial, we get f prime of x is approximately c sub 1 plus 2 times c sub 2 times x. And evaluating the derivative of our function that we want to approximate, we get f prime of x equals cosine of x. Evaluating them both at 0 and setting them equal to each other, we eventually get c sub 1 equals 1. Great. But if the double derivative of our polynomial approximation matched the double derivative of sine of x for values of x close to 0, that would be even more better. So let's do that. Let's evaluate the double derivative of sine of x for values close to 0, so that's just negative sine of x, and then evaluate the double derivative of our polynomial approximation. Setting them equal to each other, we just get c sub 2 equals 0. Now, repeating this process, let's just let the third derivative of our polynomial approximation equal to the third derivative of sine of x evaluated for values of x close to 0. Doing the math, we eventually get that c sub 3 equals negative 1/6. Now, if we were to continue this process, we would get better and better approximations of sine of x. I want you to imagine the process of approximating this non-algebraic function as a polynomial, let's call it g of x, for small values of x as a zipper. We're essentially zipping the nth derivatives of our polynomial function together, setting them equal to each other, and then finding the corresponding coefficient. So, let's just return to our polynomial approximation of sine of x, and instead of cutting it off at c sub n times x raised to the nth, we could make it a series, adding an infinite number of quantities where the terms are some form of the derivative of the function. And because of the power rule, the exponents will cascade down, creating the factorials you see at the bottom. And for the sake of clarity, let's remove the zeros. Now, how do we write this in summation notation? Well, by now, I hope you notice some patterns. Because of the periodic nature of sine of x, the terms will end up alternating between positive and negative. Also, with every term, you are raising x to an odd power and dividing that by an odd factorial. Thus, we can write this series that approximates sine of x as the infinite sum from n equals 0 to infinity of negative 1 raised to the n times x to the power of 2n plus 1, all divided by 2n plus 1 factorial. This is the Maclaurin series of sine of x, or the infinite sum of terms that approximate sine of x centered at 0. Okay, so what did we just do? Well, it's a series, so it's the infinite sum from n equals 0 to infinity of the nth derivative of our function evaluated at 0 divided by n factorial. Because of the power rule, the exponents will end up cascading down, creating that n factorial. All of that times x to the power of n, the corresponding term. This is the definition of a Maclaurin series. or a power series that approximates a function. Now, find the Maclaurin series for f of x divided equals 1 divided by the quantity x plus 3. Here's the definition of a Maclaurin series as shown in the previous chapter. The hardest part about finding the Maclaurin series is finding the numerator. So let's make a table that does just that. Now, let's condense the table to the values we need and write our series. Notice any patterns? Well, the top numbers are just n factorial, and the numbers below are powers of 3. Thus, it's the sum from n equals 0 to infinity of -1 raised to the nth power, which takes care of the alternating signs, times n factorial divided by 3 to the n plus 1, all divided by n factorial times x to the n. This is our Maclaurin series for f of x equals 1 divided by the quantity x plus 3. Now, let's find the Maclaurin series for f of x equals e to the x, or the famous exponential graph. What's special about e to the x is that its derivative equals e to the x, so the nth derivative of e to the x will always be e to the x, and evaluated for values close to 0, that'll always equal 1. So we can just substitute 1 as the numerator, and boom, we have our Maclaurin series. Thanks for watching this video. See you in the next one.